So we have now heard about agentic models, we have heard about reasoning models, these frontiers of AI innovations that are happening, foundation models, how they are changing the landscape of technology now. Um, all of these innovations are largely have been possible because of the availability of data on the internet. Right? So they have scraped the data in the form of text and images, and focused solely or primarily on data only supervision. Right? So they're apart from incorporating some form of structure in the data. Right? They are largely driven by the patterns that are there on internet scale data. And while research in AI has been powered by the collective energy of researchers in two domains, vision and language, there is an opportunity to extend our focus to many other classes of problems in science and engineering, where we have other modalities of data, right? Other forms of data going beyond observations. We have the ability to generate experiments and collect data, as Aryan mentioned. We have the ability to generate simulations that can be viewed as, in some cases, cheaper forms of generating data. And as we are seeing many of these scientific applications grow in their scale of data, um, uh, in many cases, which is unlabeled, the question that we want to ask is, how can we harness the innovations in AI to meet the opportunities in science and engineering, right? Which is again the focus of Genesis mission and several other similar directions. Right? To the extent that we have this argument or this idea or a debate that keeps surfacing at several points, which is, would black box or data only models make the existing process of the scientific method obsolete? Right? The process of building with scientific theories, starting with hypothesis, collecting data, looking at evidence for validating for those hypotheses, refining the hypothesis, and going in that loop again. So you would find these media articles that keep coming up at different points of time, right? The first one is this Wired magazine article that came out in 2008. This is far before the deep learning revolution. But even at that time, in the big data world, there was a discussion, right, of whether we are approaching the end of theory. That now that we have lots of data, can we fully embrace the complexity that we see in these data sets and do away with the scientific method? Um, the most recent article is coming from 2025, right? Scientific method versus AI. Is there still room for theory, right? Is there still room for backing our understanding of scientific systems based on scientific knowledge, right? Um, and while there is a lot of excitement in using AI for science, right, there are several limitations in the current data-only frameworks of AI that are limiting our ability to make progress in the goals that are, for example, listed in the Genesis mission. So what are these gaps? Right? So the first major gap in data-only models is that they're really good for problems where we have large amounts of data, where we have well-defined metrics that we can evaluate on benchmark data sets and measure our progress. Right? But in many scientific problems, we are looking at the need to extrapolate beyond the data that we have seen so far to new scenarios. We want to deduce theories, right, that can be applied in novel settings. Right? We want to go beyond interpolating between data samples, which is one of the powerful characteristics of AI or data-only methods, to even extrapolating to new scenarios. So what do I mean by extrapolation? Right? So there are these are just three examples of extrapolations. Right? So um, uh, even though if we have lots of data, for example, on the internet, right, we have the heavy tails of the distribution, um, uh, data samples that we do not have good representation for. For example, in biodiversity, we may have lots of images or other forms of data for humans or other animals, but we may have very few data samples for rare species that we want to detect and monitor for biodiversity preservation purposes. Right? Or we could look at precipitation extreme, right? Events that would appear once in 100 years, right? Where we would naturally have smaller amounts of data. Right? So how can we ensure that the models that we are training on the majority of data points, right, can still extrapolate to these heavy tails? Another form of extrapolation that is central to many scientific endeavors is to build models that can be applied to settings where we are changing the physical parameters. Right? So we may train a model on a certain setting of viscosity or Reynolds number or molecular configuration. And once we have trained these AI models, we want to deploy them, right, on a different setting of those parameters. The third type of extrapolation is where we want to apply these models in completely new contexts. Right? So, for example, if we look at the observation of an apple falling, right, can we come up with theories of gravitation that can then help us study the motion of planets and help us land on the moon. Right? So these are problems that are completely outside the context of objects falling on the Earth. Right? And these are problems where coming up with scientific theories helps us, and with that scientific rigor, helps us extrapolate to novel scenarios. The second major gap in data-only models is their tendency to hallucinate. Right? We are seeing that even more with the rise of generative AI models. Right? So in 2023, Google came up with this genome model that was supposed to generate millions of new molecules, materials. Right? But very soon it was found that many of these molecules that were being generated are redundant, right? Or are have chemical configurations that are not correct or do not make physical sense. So even if we are able to generate lots of samples, um, are they useful? Right? Are they consistent with existing theories? Right? Because if they are not, um, it's easy to generate new samples that are outside of the distribution of the training data, but are inconsistent with theories and hence not useful. The third major gap in current generative AI frameworks is their lack of interpretability. Even if we are able to generate new samples, can we um, can we reason to the process of how we generated those samples? Right. So if we ask for an image being generated of a fish, right, and if we ask for, let's say, the dorsal fin or some domain-specific feature of these fishes to change. For example, if we want to imagine how the fins of fishes would evolve or change with the changing environment, um, we would expect an AI model to come up with a generated sample and an explanation for why it's making those changes. Right? And that's the real driver for discovering new scientific insights and advancing our understanding or advancing our scientific knowledge. These models, as Aryan also mentioned, also have to be controllable based on the needs of scientists. Right? So we want to query them using natural language or other modalities um, to generate new scenarios, right? And to perform hypothesis testing. So while it's useful to have image generation models that respond to free-form text, can we tailor those generations based on domain-specific terminologies that we have in many scientific applications? So given these gaps in data-only AI frameworks, it's natural to ask, can we overcome these limitations by making use of scientific knowledge? And this is the central idea that we are exploring in this field of knowledge-guided machine learning, that we want to build these two-way bridges, right, where the innovations in AI are inspired not just by problems in vision and language, but also by the needs in science and engineering. And these innovations are then used to drive success in scientific applications. This two-dimensional figure that many of you would have seen several times before as well encapsulates this core idea of bringing knowledge and data together in the building of AI models. This is what we are referring to as knowledge-guided machine learning models, or KGML. And our article in 2017 that was developed at Minnesota, right, was one of the first early efforts to provide a roadmap for research in this paradigm. And since 2017, in these last 9 years, there's been a huge interest, both from the AI and machine learning community, as well as the scientific community, to explore the fusion of data and knowledge. There are more than hundreds of papers published every year in topics related to KGML. Research in this area is referred to by several names. Here are just some synonymous collections that you would hear. If we break down knowledge-guided machine learning into three components, you can use synonyms for knowledge, you can use synonyms for guided, you can use synonyms for machine learning, right? And you can mix and match, and you would find terms like physics-informed machine learning, right? Or you would find terms like theory-guided data science, which is the title of the paper that we had in 2017. Right? Or you would have science informed, science aware, science infused AI neural networks, and so on. Despite the differences in these terminologies, right, all of these works are exploring a common goal of bringing data and knowledge together. And the central objective in exploring this fusion is to address many of the challenges that we discussed of data only, or black box AI, that we want to improve OOD generalizability, out of distribution generalizability, and do that while being efficient in the number of parameters that we need and the number of labeled samples that we need. We want to make AI models more interpretable, that generates solutions that are scientifically meaningful, and also as tools that can be used for scientists to generate new hypotheses and validate those hypotheses. So this gives you an overview of the different dimensions of research that is happening in this multi-disciplinary area of research of KGML. A longer exposition of these different aspects is provided using this QR code, which is a tutorial that we gave in 2024 at Minnesota. This slide just captures few of these salient dimensions that help us differentiate different lines of research in KGML. So there are some dimensions that cater to the format of knowledge. Right? You could represent knowledge in different applications, either in the form of equations, partial differential equations, in the form of symmetries, invariances, in the form of process-based mechanistic models. You can have variations in the nature of knowledge, whether it's perfect, or whether it's imperfect, whether it's partial or complete. You can have different variations based on how you integrate process-based or knowledge-based and ML components together. You can have different variations based on how you bring knowledge in ML components of KGML, and finally, the different use cases that are enabled by KGML. So these dimensions help us look at the differences and similarities between research happening in KGML. Um, that is now spreading across a wide number of scientific applications that are some of them are listed over here. This is certainly not exhaustive, right? And you would see these circles that are representing a few illustrative research milestones that have happened in KG for different applications, right? And again, this is not an exhaustive list. There are, as I said, several hundreds papers in many of these communities. So we have a lot of research that has happened in the field of aquatic sciences or hydrology. We also have a lot of research in solving partial differential equations that started with this paper on physics-informed neural networks, or PINs. Right? We also have a lot of research, especially in the last few years, in biodiversity science with this creation of the Imageomics Institute. We have research in agriculture, climate, weather, and many other fields. So this is one way to characterize research in KGML based on the applications. Right? But we can also characterize them in a different way. Right? We can take these circles and group them based on their methodological similarities. Right? That leads us to the different research threads that are being explored in KGML. And these are some of the common research threads that cut across multiple application domains. So I'll just quickly go through a few of them that are showing a lot of promise. So one of the long-standing research directions has been on bringing knowledge in machine learning frameworks in the form of loss functions. This idea goes back to the 2017 articles, such as physics-guided neural networks for aquatic sciences and PINs for solving PDEs, where we want to guide the learning algorithm, right, with some of a loss function that measures the consistency of the model's predictions with respect to facts or scientific theories. There are different variations, as I mentioned, for solving partial differential equations. The loss is looking at discrepancy with a partial differential equation. We are looking at the residual of this equation, computed using autograd package. Or we can look at problems where the knowledge may have its own imperfections, and the knowledge may not be complete. That the equations that we are using as constraints to guide the learning algorithm do not fully describe all the processes that are happening in the scientific system. Right? So we may have some monotonic relationships between the density of water and the depth of water, right? Or we may have energy conservation principles, right? If we are trying to model the temperature of water going from one time step to another, which may have flux terms that are approximate. Right? So how do we deal with these inaccuracies in the physics itself? Right? So we have different frameworks of PGNN and PGRNN catering to these needs. And there's a lot that is happening on how do we sample in the space of data points. How do we balance the importance of prediction loss and knowledge credit loss? Another major research thread in KGML is pre-training with simulations. That if we have a process-based model that is able to generate inexpensive simulations that we know are approximate, can we use them as a starting point? Can we use those simulated data points to pre-train an AI model that can then be fine-tuned on observational data using very small number of samples. Right. This is the framework that was explored in physics-guided recurrent neural networks (PGRNN), and it's connected to this idea of sim to real problems that people study in the physical AI community. Um, the third research direction is that once we are able to train these models, either using simulations or using loss functions, can we also use knowledge after the training process, right, during inference, right? So Aryan mentioned about iterative refinement, right, or test time refinement. How do we bring knowledge to influence the generation of data points or the predictions during the inference process? Right? And these models could either be domain-specific models, or they could also be frontier AI models for vision or language. Right? So there is this popular framework of retrieval augmented generation that explores one path, right? That if you have LLMs or multimodal large language models, along with just feeding the prompt into these models, can we also look at the relevant documents that we may have in a repository and improve the context of the prompt by looking at the relevant documents, so that our response is guided by the knowledge, the local knowledge in the retrieved documents. There is also work in using iterative refinement, which is a remarkable capability of diffusion models, as Aryan mentioned, and steering them during inference using knowledge guidance. So I'm not sure if this slide is visible, but you can see that there is in this example work of diffusion PD. Okay? What was explored is that you can train a model using no knowledge of the underlying PD, right, for some physical application, and that can be prompted with sparse observations. Right? But during the inference process, right, you can use the PD guidance as a loss. Right? So you can perform gradient descent as you're iteratively refining your solution, where the gradient is being computed of the physics residual or the PD residual. The fourth major direction, and actually it's a cluster of directions, is going beyond the use of loss or training strategies and changing the architecture of machine learning models itself. There are different clusters of ideas that people have explored. One of them is incorporating our knowledge of the dependencies between different physical variables in a scientific system in how we design AI models. Right? So we can have AI models that produce intermediate features, right? That can then be combined in physically useful or interpretable ways to generate the final target variables. Or we can have modular structures where these modules that we are using in an ML framework mimic the modules that you would see in a process-based framework, and you can replace those components or those modules that you know are lacking in the process-based model. So there are different directions on incorporating knowledge in the form of dependencies of variables. You also have a lot of research on incorporating inductive biases in AI frameworks based on our knowledge of symmetries. A classical example is that of a convolution neural network that is invariant to translation in space. Right? So regardless of where you place a cat in an image, either on the left or the right side, you would detect the presence of a cat. Right? You can also have concepts of equivariance, right, where you want to, for example, if you're segmenting the cat, right, you want to, if you have learned a model to segment cats on the left side, you can apply the same model to segment cats in images where the cat is on the right side. The idea of and you can see that these popular deep learning frameworks, it also inherit these inductive biases that are coming from our knowledge of the structure in the data. The idea of temporal invariance, that we can use the same set of parameters to model the temporal dependencies going from one state to another is expressed in the form of RNNs, LSTMs, right? But we can go beyond uh, the spatial and temporal invariances to look at rotational equivariance. We can look at high dimensional spaces, EN, forms of incorporating symmetries that are especially important for molecules and other applications. The third subgroup in incorporating biases is in our knowledge of similarities or distances between data samples. A popular example is the framework of AlphaFold, where we are interested in looking at similarities between different protein sequences. Right. So the backbone of the AlphaFold is the Evo Former architecture, and the 2021 version that came out, the first version that came out, explored this idea of using attentions that is informed by multiple sequence alignment, right? That would capture the evolutionary signal to decide whether two sequences are similar or not. Right? Um, Similar ideas are being explored for biodiversity science or organismal biology, where we are interested in representing every species, right? They could be animals, they could be plants, they could be viruses, based on their similarity in some hierarchy. It could be the tree of life, the phylogeny, which drives their evolution, or it could be taxonomic groupings, right? Genus, family, other higher order groupings. So can we learn representations that are guided by these similarities? So this is another major direction. There are many other directions. You have concepts of operator learning. You have concepts of differentiable modeling, where the AI model is embedded within a process-based framework, right? And we are exploiting the differentiability of process-based models to learn these AI models. This shows you the diversity of research that is happening in the different threads of KGML. But an important question is, how does it relate back to the central goal of today's workshop, which is GenAI for science? As we see these AI models becoming more proficient at generating code, right, or even helping with solving math problems, right? Have we, as these models grow in their generation capabilities, as we scale them with more data, with more parameters, have we solved the problem of accelerating scientific discovery? What we see is that um, as we scale these models further, and as we see their capabilities growing, right, the challenges in using data only methodologies that are driving GenAI only become more apparent. So the same challenges that we mentioned, generalizability, hallucinations, interpretability, controllability, become major roadblocks when we have to go beyond generating samples that not only look realistic, right, but are also useful for science, right, that are consistent with scientific theories, that are novel and useful, right, that are controllable based on scientific queries, that provide the right reasoning, the right explanations, and that are also amenable to planning, right, which is the idea of world models. So how can we achieve these goals? um, uh, by looking at KGML. How can we incorporate knowledge in the modern GenAI frameworks that we discussed? Right? So here are some of the directions that are being explored, and I'll quickly go through them in the interest of time. Um, uh, there's a lot of work that is happening in designing architectures of GenAI inspired by knowledge, right? So we have already discussed examples of symmetry-aware architectures, attention mechanisms that are guided by knowledge, for example, in AlphaFold. We have also discussed structures that are modular, that mimic the modularity of process-based frameworks. So, and some of these ideas are being explored uh, completely independently in the AI community too. For example, the hierarchical reasoning model that came out last year that got a lot of media attention because this is a model that only had 27 million parameters, but was able to outperform the state-of-the-art models with trillions of parameters. That is exploring this idea of modularity and model reuse. Can we align these models that we are using with processes that we already know in science? When it comes to architecture design, a central focus is on learning representations that are structured with scientific knowledge. This is especially useful when we are applying models like diffusion, where we can think of uh, structuring the conditioning space of these models so that they align with scientific queries. For the problem of biodiversity science, this is one work that was done by my student Mridul, where we are using knowledge or phylogeny guided representations of species as inputs into a diffusion model to generate images of species that exist. But we can also use these conditioning spaces to perform experiments that are similar to the transformation that you would perform in Word2Vec, right? That we can mask out certain portions of these conditioning spaces and see what changes in the space of images, right? Or we can perform experiments similar to gene swapping, but now in the space of or the conditioning space of images. And all of this is leading to novel scientific hypotheses. We can look at these generated images generated by these perturbations and see um, uh, what is preserved in the image space, what changes. And all of this is only generating novel hypotheses, right? That still have to be validated by scientists. There's a lot of work or there's a lot of potential for advancing self-supervised pre-training strategies using scientific knowledge. For example, using loss functions that are knowledge informed, or rethinking the backbones of many generative models, for example, diffusion models that are based on non-equilibrium thermodynamics. Can we think of other forms of forward models beyond the addition of Gaussian noise to generate diffusion models or diffusion style models? Can we use simulations to pre-train these models? And another important question that Aryan explored is how do we get the right mixture for pre-training GenAI models? How can we leverage our knowledge of similarities in data samples based on physical parameters to sample diverse data points? There's a lot of work that is happening on the post-training aspect, guided by knowledge as well. I mentioned diffusion PT, which is an example of a posterior sampling method. So we're looking at the posterior distribution of these models and guiding those posterior distributions based on physics knowledge. The challenge with many of these frameworks is that they still need to perform gradient descent during inference, right? And they need to compute gradients of expensive PD residual calculations. In our recent work done by my student Medha, we have explored how we can avoid the computation of physics gradients by changing the architecture directly by using spectral attention. So this is knowledge-guided architecture design, such that once trained using physics knowledge, they can be applied during inference without any expensive gradients, which is leading to several magnitudes improvement in the inference speed. Um, Another avenue to explore in generative AI is knowledge-guided reinforcement learning that Aryan described in detail. There is a lot of opportunity to design reward signals in reinforcement learning that is guided by knowledge. That may come in the form of loss functions, in the form of simulations, consistency with scientific literature, or expert preferences that is driving the RLHF framework. So with that, I'd like to conclude. Here is just a summary of the different GenAI methodologies that we discussed that can be enabled by KGML and how they are helping us arrive at or at fixing the gaps that exist in current GenAI frameworks, right? Of interpretability, reducing hallucinations, or generalizability and controllability. So with that, I'd stop and happy to take questions.